Nuclear reactions. This topic um, is, again, a whole field of science onto its own. We're going to barely scratch the surface. What I want to uh, really focus on is the aspects that a basic understanding of what's going on, and then talk about how it applies to the medical field, since this is for health sciences. So there's some radiation types in terms that get thrown around in common parlance, and we just go with, okay, it's some mysterious thing that's unseen that can maybe hurt us, maybe not. Yeah. So let's look at some of those terms to start with. We have microwave radiation, which everyone's pretty familiar with. We have Most of us have microwaves in our house. It's electromagnetic radiation, and it can be used in cooking food, obviously. It's also used for communication, though. Uh, Broadcast transmissions for like radio stations are typically microwave. Um, Engineering and navigation use microwave radiation. I'm not really sure how the applications there go. Again, other than transmissions, yeah, I'm not into that field. Don't know. Infrared radiation. Electromagnetic radiation that cannot be seen but can be felt as heat. Okay, again, most of us are kind of familiar with having experienced that, at least in some form. Ultraviolet radiation we hear a lot about because that is what can cause skin cancer. We know if we get too much, we get sunburn. So this is a high energy electromagnetic radiation. And of course, in the medical field, in anybody even not in the medical field, most everybody's had an X-ray at some point in their life, and that's also high energy. It's an ionizing radiation, and we'll discuss ionizing radiations a little later, um, soon. Okay, it's similar to gamma rays. Well, okay, that doesn't mean anything. What's a gamma ray? Okay, um, and they are produced in X-ray tubes. Okay, so then the next one we have is gamma radiation. It's a naturally occurring high energy electromagnetic radiation similar to X-rays. Oh, great. X-rays are similar to gamma rays, and gamma rays are similar. It's like, that doesn't tell me anything, does it? With a high penetrating power. Okay, we know they both penetrate. So maybe by the time we get done talking about um, what kind of particles exactly make up these radiation types, maybe you'll have a little bit better picture of what some of this stuff is. Okay. But those are standard definitions given. It's kind of like, well, they refer to back to each other. And if you don't know one, then you don't know the other. And right. Okay. So radioactivity is defined as the spontaneous emission of particles or energy from an atomic nucleus as it disintegrates. Atomic nuclei disintegrate. Okay. You probably know this. You're thinking, no, I thought we had to make it happen. I thought we had to split that hydrogen atom to make the H bomb. I thought we had to, do something weird to uranium to get nuclear energy out of it. I don't. Uh, yeah, no. Well, yes, but again, as I tell my biology students a lot, and I probably said it to you before too, um, we humans really haven't created anything new and novel. Okay, we observe what happens in nature, and then we imitate it, or we maybe modify it a little to use for our own purposes. So, radioactive decay is something that occurs naturally, and we have, in over time, learned to manipulate some aspects of that. Okay, so we have types of radiation. We have alpha, beta, gamma, something called electron capture, positron emission, and then spontaneous fission, which that's a rare thing. It's a really, from what I've read, it says it's a really high energy, high mass atom that has to have that certain circumstances for it to happen. So I think it's rare in nature, but um, that's what we have learned to manipulate. That's what we learn to manipulate in a small mass atom for the um, hydrogen bomb. We didn't get it to spontaneously do it. We did have to trigger it, but it's fission. Okay, but it does happen naturally in a spontaneous version, just not with hydrogen. Okay, uh, so let's go through these different types. First, we have alpha decay. uh, alpha emission, an alpha particle is going to be emitted, and alpha emission is an expulsion of an alpha particle. It's like, well, great, alpha decay, alpha particle, alpha. What is that? Okay, an alpha particle is the nucleus of a helium-4 atom. Okay, so that is a helium that has 2 protons and 2 neutrons. Okay, which is your standard isotope. Okay. All right, remember, just go look at your periodic table. What's the weight of a helium, natural standard helium atom? What's okay? So yeah, so we're not talking about anything really weird here, except that it's had its electrons stripped off of it. Those 2 electrons aren't there. This is just the nucleus of that helium atom. And this particle can travel from 2 to 12 centimeters in air and can be stopped by a sheet of paper. So doesn't actually travel very far because 12 centimeters is not even a full a ruler, a 12-inch ruler where English measurements used to is 30 centimeters. Okay, so you're talking then less than that's 12 inches, less than 6 inches. Okay, at max it'll travel, and a sheet of paper is going to stop it. So not much penetrating power here. Okay, but that is a type of radioactive decay that happens. And note this, we're going to get into this a little bit with some problems. Emission of a helium-4 nucleus that contains 2 protons and 2 neutrons. But that protons, what do protons do? Remember I gave that my alchemy talk back at the beginning of the semester? So trying to change one atom into another, one substance into another, couldn't be done, but oh well, maybe it could be done. Well, if we could just get things to gain or lose protons, we could change things. We could change the identity of the atom. So here in radioactive decay, we've got identity of an atom changing. Okay. So we've lost 2 protons here. That's going to change the identity of that atom. Neutrons, it doesn't matter, but protons, that matters because that's what gives the identity. So more on that. Let's talk about our decay types though before we get into it. Beta emission, that's the expulsion of a beta particle at high speed. A neutron is split into a proton and a high energy electron, that's the beta particle, is given off. I didn't finish that sentence, did I? Okay. Um, adds 1 proton to the nucleus of the atom. Okay, so here we see carbon. It's carbon-14, isotope of carbon, and addition of a proton, and that's going to turn it into nitrogen. This is uh, a calculatable standard rate decay that is used in carbon dating. This is the carbon-14 dating. Okay, we can look at the ratio of carbon-14 to nitrogen in something that was once, this organic matter, and we can determine how long it's been dead. Okay, uh, so because the carbon-14 to nitrogen ratio in a living thing is a set ratio, and as that ratio changes, we can calculate how much time has happened since the death of that organism. Okay, all right. So you see, travels several hundred centimeters. Okay. So a meter stick is 100 centimeters. So um, it could travel a meter or 2, several, 3. Okay. Uh, it is stopped by a thin layer of metal or aluminum, 1 centimeter thick. Okay. So a little bit further travel distance, a little bit further, a little more penetration power. Gamma emission is a high energy burst of electromagnetic light, or a photon. It's not detectable by the human eye, can travel through the human body, but it can be stopped by a 5 centimeter thick piece of lead close to the source. Okay, this is just light, no protons, no neutrons. We have nothing going on here, just light given off. Okay, that we can't see, right? Photons, we can't see them, but so no, yeah, no weight, just energy. Electron capture. This is where an inner shell electron, not one of the valence electrons out there that get involved in reactions and stuff, chemical bonding, but an inner shell electron is going to combine with a proton in a nucleus to form a neutron, and that releases an X-ray. Okay, so there's where the X-ray source is. Now, what happened here? Let's just what happened here. We had a proton change into a neutron with the help of an electron, of course. But that means this particular atom, as it decayed, has lost a proton, gained a neutron, lost a proton. So its identity has changed. Positron emission. A proton splits to form a neutron and a positron. And positron is like a positively charged electron. It has the same properties basically of an electron, except it's positive charge instead of negative charge. And it gets released. The positron is released. Okay. And so, okay, let's look what happens here. A proton is split. Okay, we're going to lose a proton again, and we're going to get a neutron out of it. So we've changed identity again. This is used in medicine. The positron emission tomography, PET scan. Okay, it's probably where you've heard the term before, PET scan, or will hear it as you go on through your medical training. This is where the where that energy comes from. Okay, so the positron energy is emitted from this type of decay. So periodic table, because, excuse me here, sorry, adjusting my microphone. Periodic table, you have to use a periodic table in calculating nuclear decay and figuring out what's going on. Okay, and so let's do a few nuclear decay problems because there will be something like this on the test. So let's see, I have gone with a dark background again. Let's go with yellow, I guess. All right, so we're going to look at potassium. And potassium is number 19 on the periodic table. And it has an atomic mass of 42, rounded. Okay, and we can look back at the periodic table if you need to. And I'm going to be going back and forth this periodic table, I know, so just get used to going back and forth to it. Okay, 1942. Actually, the periodic table here says 39. What's up with that? What do you think? Well, if you remember back earlier in the semester, you say, well, that's just an isotope of potassium, different from the average isotope, the standard isotope. It's an isotope. Okay. So, and if you thought that, you are correct. Okay, you're thinking right here. So back to my drawing pencil here. So we're going to say that it emits an electron that is designated as 0 because electron has no mass. So you always see that there. And a -1. So we know it's an electron. If this were a positive one, we'd be looking at what? It's a positron. Okay, but this is an electron, standard electron that you're familiar with. Okay, we haven't really talked about positrons, so that's kind of something new for you. All right, so it's going to emit that. And something else, right? So this is decay. You start with one thing, you break down, and you get something else. So this be your question. What are you going to get? So let's go back and review our decay types. Start at the beginning. Okay, so alpha emission gets us expulsion of an alpha particle, which is a nucleus of a helium-4 atom. So nope, we're not that. Expulsion of a beta particle at high speed. A neutron is split into a proton and a high energy electron? Well, we've got an electron, a high energy electron. Could we be getting a proton off of this? Hmm. That sounds like that fits. Sounds like that's what we've got here. That sounds like that's a beta particle, doesn't it? Okay, let's see what our other because we have here a high energy burst of electromagnetic light. It's a photon. That's not an electron. It's just that's energy, light energy that we can't see. Okay, electron capture. This is where an electron is going to combine with a proton to form a neutron. That doesn't look like that's what's happening in this equation. Positron emission. Okay, well that'd be a positively charged electron. That's not what we're seeing, and that's it. Okay, because we're not going to talk about the spontaneous fission. Okay, it's not part of our discussion here. It is a type of decay, but it's not one we're really um, focusing on. Okay, so it's got to be alpha. Um, no, not alpha. Beta. Sorry, it's got to be beta. This is a beta particle, um, and so we are going to have one proton added to the nucleus. So what's that going to do? It's going to give us a 20 here. So we have to be calcium now. Okay. And so that's going to be it's calcium, and that's 20. That's our proton number. It's our atomic number. Have we had a change in neutron number with alpha decay? Does that do anything to our neutrons? Went back too far. No, it didn't. There we go. Sorry, I keep saying alpha. With beta decay, I think I meant to do an example. I meant to do examples in order, and I just jumped in with this one instead. Okay. Uh, so let's see. Um, a neutron is split into a proton and a high energy electron. Adds a proton to the nucleus of the atom, but it would indeed take us down one neutron, wouldn't it? So this would then result in being a 41. No, it wouldn't. Why not? Tell me. The weight's the same. We've changed the number of protons, but we lost a neutron, we added a proton. Okay. So be careful about that. It's deceptive. You say, oh well, we lost a neutron, so we got it. Yeah. Okay. So the atomic mass has stayed the same. We just had we lost a neutron, gained a proton. Okay. Okay, let's look at a different example then. Let's go with let's go with the plutonium. Um, and plutonium is atomic number 94. And this isotope has an atomic weight of 239. And it's going to decay. And when it decays, it's going to give off something that is notated as this. Okay, can you recognize that? What kind of particle that is? It's a helium-4. Okay. Uh, and you say, well, it just looks like a standard helium. How do I know it's just a nucleus? Well, because we're doing nuclear decay. Okay. Uh, and of course, it's going to give off something else. So what would that something else be? So let's go look at our periodic table again. And of course, what type of, well, yeah, just about said it. What kind of decay is this? Okay, our helium-4 atom are with 2 protons and 2 neutrons being given off, okay, is to make up the 4, 2 protons identity. Okay, 2 protons, 2 neutrons total add up to 4. That is an alpha emission. This is an alpha particle. That can be a question. What kind of particle is this on, on the test? Yeah, or which of the following is designation for an alpha particle, beta particle, gamma particle? Probably not gamma particle because that's a photon, but that could be a word you could choose. Wouldn't necessarily be a symbol. So, okay, back to our periodic table then. Let's look and see what that does to us. If we've got plutonium down here, 94 at the bottom, and we lose 2 protons out of it. It's been given off 2 protons. What's left? Okay, let's just count backwards. 1, 2. It's going to give us uranium. Uranium's atomic number is 92. Okay, so our 2 plus 92 plus 2 is 94. Okay, check yourself there. And then, of course, what does that do to our atomic mass? Okay, so here we have lost. We don't have anything changing from one form to another or anything like that. We just lost 2 protons and 2 neutrons. So that means that this number is going to go down by 4. So we're going to have 235 as our mass. It's supposed to be referred to as uranium-235. This should be called plutonium-239. Okay, yeah, helium-4, yeah. Just designating which isotope of this atom we're talking about and dealing with. So, hey, let's talk about that uranium, right? Because that's one that we're quite interested in, have been for a number of years. What happens to it? And this is something that happens. You have one thing decays into another. Things decay because they're not stable. They're an isotope that is not a stable isotope. So, and over time, almost everything becomes unstable. Okay, uh, everything's got a half-life, put it that way. I was looking at periodic tables to put up here in this slide, and I ran across one that said periodic table of radioactive elements, and I'm like, well, what's not on there? And everything was on there. Okay, some have just incredibly long half-lives. Okay, so let's just keep it right there. Uranium 235. Is going to decay. Now, what do you think? Do you think it'll undergo the same type of decay? Yeah, they will. Okay. Now, there is another designation for, so go away. Okay. There's another designation for an alpha particle, by the way, because, the Greek symbol for alpha is this. And so you can see that, and sometimes it'll have the numbers this with it. So that's another way of designating an alpha particle. So to answer my previous question in a different way, saying that, well, you just know that that's only the nucleus we're talking about because we're doing radioactive decay. Well, if you needed to be more clear, wanted to be more clear, then you would just use this, and that tells everybody it's an alpha particle, not the whole complete atom. Okay. So that's an alternate there. And so if that happens, what's that going to be decayed into? And what I really should have done is I should have told you what it was decayed into. I mean, I should have told you this and asked you to come up with that, but I didn't. Okay. Um, so let's go and look. We've got uranium. We know we're going to lose 2, right? two protons, so 1, 2 gets us to thorium. And thorium's atomic number is 90. And we're going to lose another 4, 2 protons, 2 neutrons for a total of 4 lost in atomic mass. So that's going to be thorium-231. Okay. All right, so that's enough alpha. We've done alpha, we've done beta. I ought to do a positron emission, if I can find an example. Okay. Let me just clear my drawings here. I don't know that I have an example of electron capture offhand. Let's see, that's a... Yeah, so pretty much all the examples that I have on worksheets that I have given in the past, which is what I've taken my test questions off of in the past, so that's probably what you're going to get, are pretty much alpha and beta decay questions. It's like, now I know I've got some difference. Oh, I have a fusion reaction. To give you an example of fusion reaction. So, yeah, I didn't define that, so I don't think I'm going to talk about that one with you. Here is the reaction for actually how uranium is used. Okay, which I think is interesting for you to see. Okay, so you got uranium-235. And of course, its atomic mass is 92. Okay. And what we do with that is we bombard it with a neutron. Okay. So it's distinguished as like having negligible mass. It's got a weight of 1. Okay. And that triggers the reaction. So I was mentioning triggering reaction a while ago. Okay. And when we do that, we get barium, which is atomic mass, or atomic number rather, 56. When it's got an atomic mass of 142. And we get krypton, which is atomic weight of, or atomic number 36 and atomic mass of 91. Getting sloppy as I go, like normal. So I get tired. It seems like as the presentations go on, I get sloppier with my writing. Okay, and I'm probably gonna wrap it up here shortly. It seems like I'm looking through my sheets here, thinking there's something more I need to add. But okay, there's something missing though. Let's look, because you start adding these up and they don't add up exactly, I don't think. Let's look at that. Let's come over here and just do it, so I don't get in trouble with doing math in my head and not carry a number and mess it up. 233. So something's miss, right? Missing something. Well, it can't be protons, okay? Because I'm telling you, these are what we get. Okay, we know the proton number in those. So, and those do actually add up to 92. So we've got to be missing some neutrons, right? Well, there's two right here. Okay, if we take 233 and subtract from 235, that would get us two neutrons. But that's not the answer, because just like every balanced equation we've done in stoichiometry, everything on this side, mass is neither created nor destroyed, matter is neither created nor destroyed, everything that's on this side of the equation has to be over on this side of the equation too. And though between here and these two, we're missing two neutrons, what happened to this neutron? Did it disappear? Okay, we just used it to trigger the reaction. It didn't get consumed. It didn't disintegrate. It didn't go away. It's still there. So you account for it here. Okay, so three neutrons. You start off with one. You get these two atoms produced as this nucleus breaks down, and you get and so this is nuclear fission. I said I wasn't going to talk about spontaneous fission, but here's triggered fission, which is, it's us mimicking, us triggering a natural process. Okay, so um, we wind up with three neutrons, and that's why this is called a chain reaction, is because three neutrons, and if you've got your 235, you got uranium 235 there with three random neutrons ready to bounce into it, boom, you're going to have what started off as one atom reacting now is three, and then each one of those reactions will produce three. So then the next after that reaction will have nine, and it just chain. Okay, chain reaction. So uh, that's the uranium radiation, the uranium decay reaction, if you were ever curious. Okay. Um, let's see. I know there's another example somewhere. I'm just missing it that I want to talk about. Um, did beta, did gamma. I think that's really it. I'll be giving you questions, a few of different types of problems where um, you're going to be experiencing um, beta decay, alpha decay for calculations. The others are just recognizing the types of uh, particles. Okay, and that'll be enough. Clear that. That'll be enough for you. Um, yeah, potentially we could go into more detail, but we've got a few more other things to talk about here before we're done. And so let's move on to that. So other things that you're going to be encountering in the medical field would be probably these terms of REM and RAD. REM is radiation dose, the amount of radiation received by a human. And RAD is when we're talking about materials, how much radiation was received by a material. So just different terminology. Think a different base unit, okay? We also have background radiation. It's ionizing radiation, alpha, beta, gamma, of the types we just talked about, that comes from natural sources, between 100 and 500 millirems per year of exposure to natural radioactivity from the environment. If you watch the little film that I've got attached to this section by Veritasium, it's a really cool film where he goes around to the most radioactive places on Earth. He will talk to you about background radiation in terms of a banana. Okay, it's just really cool and interesting, and I'm really fond of the Veritasium videos. So um, it's fun and cool, and there are some test questions on that film. Okay, because the standard semester, and I was going to give you online tests or online quizzes over this, and it's just time. Me trying to get all this stuff filmed and get papers graded and your stuff transferred, all the grades transferred on online because I didn't have them there to start with. I've fallen behind. So this is spring 20 class where we had to transition because of the virus. So I didn't get around to that. And you're not going to have to worry about taking those quizzes, but there will be some questions on the test over that film. So do watch it. Take some notes on, uh, who receives the most radiation. Okay, who on this planet, or what humans, okay, receive the most radiation each year. Um, and then other things that are talked about in the film really apply to some of this other stuff that we're getting to here in the next few slides. Average background radiation is about 0.27 rem per year. A dose of less than 25 rem generally produces no detectable biological effects. Okay, so that's not 0.25, that's 25. So our average background radiation is not even 1/25th, not even really 1/50th of what would cause a biological effect on us. Okay, but a single dose of 25 to 100 rem causes a temporary decrease in white blood cell count, and this is why if you are treating someone who is having to take a lot of scans of different types and be exposed to different types of radiation for different types of scans, or even the same type of scan over and over again, you've got to make sure that you're checking the paperwork, okay? Because nurses are going to catch the doctors. Doctors are they're busy, and I've always told my students this, and I tell you this already. I've told you in class that you're the one that's probably going to be spending more time with that patient. For sure, you're going to spend more time with that patient than the doctor, and you're going to be more familiar with their paperwork. And so it's part of your responsibility to check, okay, and catch these things. Now we have the database, the national database where all this stuff gets entered in. It helps a lot with that, I'm told. Okay, I'm not a nurse. I'm not into that field enough to know exactly how it impacts, but I would imagine it helps a lot, and I'm told it does in catching things where one doctor prescribed one type of X-ray or scan, and then another doctor did another one, not knowing the other one had done it, and the person got a lot of radiation from different sources, and that just hurts the immune system. Okay, and can do other tissue damage as well. A dose of more than 100 rem produces symptoms of radiation sickness. What is radiation sickness? What are the symptoms? You can have nausea, vomiting, fatigue, and prolonged decrease in white blood cell count, which means your body can't fight off the other illnesses. And of course, like I said, we just have the tissue damage to the cells themselves. So there's a term called LD50, and you're going to see that again more and more. if I'm sure you're going to see it in, in microbiology class, and I think you actually have to calculate it in micro. Um, and because I'm pretty sure I had students calculate it when I taught that. Uh, oh, in nursing school, I know you will um, have to understand it, have good understanding of it. Back on, I think on our first lab, one of our pre-labs, I asked you to look up the LD50 of a few chemicals. Okay, and so that's the lethal dose that kills 50% of the population. Of what's being tested is mice that we extrapolate to humans. In certain circumstances, we have, unfortunately, actual human data where people have been exposed to things they shouldn't have been. For radiation, we're looking at disasters. We've had nuclear disasters, uh, and purposeful. Okay, Japan, we released some bombs on them in World War II, and then that unfortunately provided data for how radiation affects people long term, and kind of what amounts are LD100 and LD50. The Chernobyl accident has added to that data, and that's one of the places that he visits in Veritasium. So, kind of, like I said, it's an interesting little film. It's not very long. I think you'll enjoy it. Uh, so the LD50 for humans is 500 rem, and the LD100 for humans is 600 rem. Okay, uh, but okay, from 25 to 100, we can see ill effects. Okay, but it does take 100 or more to produce radiation sickness. So somewhere between 100 and 500 is where you die. Okay, just because 500 kills LD50 doesn't mean that that's safe. Okay, that means half the people exposed to it die at that rate. Some people are possibly going to die with only 100. Okay, radiation sickness sets. I mean that's enough of a damage factor that you're starting to get symptoms and can cause death in some individuals. So yeah, anywhere over that. So that's what you got to look out for and make sure that you're keeping people, in a uh, the safer range, and only the radiation that is important for diagnostics, and taking into account that some jobs, and that'll be mentioned in the film too, some jobs expose people to higher levels of radiation than just this background radiation. Okay. All right. So that's it for radiation and nuclear decay and radioactivity.